First of all, I would like to thank very much all the organizers for the honor of being in this event for Frank, and also for organizing such a wonderful conference, and to all the other speakers as well. And to Frank, well, I mean, thank you for all the mathematics that you do, and I think that you know, sort of I learned not just like you have exquisite taste in mathematics, but also exquisite taste in wine, which is, I learned both of them. And I feel a little bit weird because a little bit, in some sense, my talk is a little bit transversal to your work. But here we go. So what I would like to talk about is about a sort of invariant Gibbs measures for 2D NLS and for 3D cubic nonlinear wave equation. And sort of there are like two goals here. One is in the context of NLS, I would like to introduce the method of random averaging operators, which allow us to solve sort of an open problem since Bourgain's work on the 2D Gibbs measure. And also the theory of random tensors, which is kind of like, if you wish, like an analog to part of the theory of regularity structures, but for dispersive PDE, and which also allow us, in the same way as regularity structures, to actually prove local well posedness in the full range of subcritical range for that. And both of these are work with my great collaborators Deng and Haitian Yue, who was my student. And the second part, I want to talk about a big problem that was open, which is kind of like the hyperbolic, what is called the hyperbolic phi-4-3 model. And this is simply the invariance of the 3D Gibbs measure under the cubic NLS. Everything is periodic. Sorry, NLW, thank you. NLS is still open. This is like a Freudian slip. All right, so everything, I'm always in the periodic box. And this is a joint work that we have done with Bjoern Bringmann, who joined us, and was crucial that we had him with us. Okay, so let me use this hand because I can use this one. So everybody knows the NLS. This is, I'm going to consider NLS with any power nonlinearity, which is going to be odd, always bigger or equal than 3. Equation is going to be defocusing. And as everybody knows, the deterministic scaling for this equation is d over 2 minus 2 over p minus 1. And so maybe a meta theorem that I would like to say is that what is known is that if this number is non-negative, then the equation is locally well posed for any data in HS as long as S is strictly bigger than this critical scaling index. And ill-posedness may occur if you are below. And okay, I put some of the works on that here. And so what happened in 1996 is that, you know, historically people knew about the existence of weak solutions if you wanted to cross the scaling barrier. But in 1996, Bourgain showed that if you consider, instead of every possible data in HS, but you consider sort of like what is canonical random data, sort of or samples from a Gibbs measure, which is what he was studying, then for some S below this critical index, one can almost surely, in the sense of probability, get actually strong solutions. Okay, and this was like a great breakthrough. So by, say, canonical random data, what I mean is simply that you take data of this form. So GK omega series are IID complex Gaussians, or they could be uniformly distributed on the circle. And so the law of this random variable is formally given by a Gaussian measure, which sits in HS minus, where S minus is this alpha minus the dimension over 2. So I need you to remember this relationship because it's going to come over and over. And for in 2D, where he was interested, or for sort of like a Bourgain, so the statistical ensemble of the Gibbs measure corresponds to alpha equals to 1, and I'll come back to that later. So, so the random data problem, sort of like after Bourgain, was studied by many people, most prominently by the work of Setkov and Burke and Setkov in the context of nonlinear wave equations, and there were many results sort of like following Bourgain's work. And we can view all of that as actually the study of, or I would like to view it as the study of how randomness propagate under the flow of these equations. So in other words, you start with some random initial data that is distributed according to some canonical law. And what you want to know, you assume that you have independent Fourier coefficients, because it's distributed by Gaussian, says independent Gaussians. And then you want to know how this random structure propagates as you move along the flow. Okay, so in other words, what happened? I mean, how much of the random structure survives, for example. And so these are natural questions that you can ask, or some of them is, what is the optimal range where the solution exists and is unique, almost surely, at least for short times. Can you give a description, a precise description of how the solution looks like? Not just like it exists, but how does it look like, at least for short times. And if you have a Gibbs measure, then which is defined, has been constructed, it is known, and it's sort of formally invariant. The question is, can you rigorously justify its invariance? So, as I said before, there was a lot of works. There was a lot of papers by many people, and I didn't put. I tried to put all the names, but it's like it would be at least like a slide and a half. I cannot read them all. But there is always this feeling that people could push, would use Bourgain's method to push, sort of like a random data local well-posedness below the deterministic scaling of the equation. But it's kind of like, you could go a little bit below or lot below, but it was never clear what's the threshold. I mean, it's like, what's going on there? And I was very interested in, for example, the question of the invariance of the Gibbs measure for the quintic NLS in 2D, which was an open problem Bourgain was very interested in as well. And if you look from the deterministic scaling, the quintic NLS in 2D and the cubic NLS in 3D, they both have the same scaling, which is a half. But while one problem actually we succeeded in solving, the other one is like an impossible. It's like really much harder. And so the reason is why. I mean, you can sort of like say, oh, well, the method, counting estimates, this or that, but none of those answers are very satisfactory. Okay? And so what we sort of did with Yue, Deng and Haitian was like think about this and realize that actually the right lens or the right scaling in which one should actually look at these random data problems is not a deterministic scaling, but what we call the probabilistic scaling. So what are the heuristics of this? The heuristics is that you take, say, let's suppose that you take random data, which is sort of homogeneous, all the frequencies are of the same order, n to the alpha, and you normalize it so that this random variable has unit size 1 in HS. And then you ask like the most basic question, which is that if the equation is going to be almost surely local well-posed, then the second iteration of this, or whatever, the iteration of this should be also in HS. That's what you should have, right? And so you write the Fourier coefficient of this object. This I is the Duhamel operator. So you write what is the Fourier transform of this object, and that's simply of this. And that's simply n to the minus p times the sum over k1 minus k2 plus kp. OK, that's because you have complex, this is bar. So the minus is when you have a bar and the plus when you don't. And all these coefficients are of the same frequency, as I said, n. And omega is just the resonant factor corresponding to NLS. And plus minus here, as I said, represents whether you have a bar or no bar. And so suppose that you restrict yourself to omega being like a constant or 0, whatever you want. And let's assume that these are always state independent, which just means that k1 is never k2. The bar and no bars are never equal. And so then what you ask is, you say, well, if I want this to be in HS, then what's the size of this? And what you realize is like, you say, well, if I just count, if I just do a dimension counting of this and I forget the Gaussians, if all of these were ones, then dimension counting will tell you that the size of this sum, the sum over this with these conditions of 1, is simply n to the pd minus d minus 2 without the 1/2. And when you have the Gaussians here, this is like in the central limit theorem, you have this square root cancellation gain that puts a 1/2 on the counting of this object. And so when you put it together with this, what you get is that then in order to stay or remain in HS, you need S to be bigger or equal than -1 over p minus 1. And this is what we call the probabilistic scaling. And as I said a minute ago, if all of these, oops, sorry. I cannot use my right hand, sorry. If all of these were 1, you recover your deterministic scaling, okay? So the point is, okay, if this is a guiding principle, means that this in principle, I mean, this doesn't mean that this is always a threshold between local well pulses and ill pulselets, but it's sort of like a guiding principle that tell you that, well, you know, if you're going to be local well pulsed, the best you could do is this. And actually, this is what we proved for NLS, and what we proved with Deng and Haitian was that if S is strictly bigger than this threshold, this is the full subcritical range, then the NLS on the periodic domain for any power p, this is completely unified. So this is for any p odd in any dimension. And you should note, maybe you wonder, the probabilistic scaling is independent of the dimension. Then we always have strong solutions, unique strong solutions, and we also can give a very precise description on how this randomness propagates for short times. So I will describe what I mean by this a little bit later, and in the meantime, meanwhile, I want to sort of take a little bit of a detour on Gibbs measures, which was actually a theorem that we proved before this. So in some sense here, we are answering, except for the Gibbs measure question, we are answering the first 2 questions that I posed before. Okay. So some remarks. Okay, so I'm ignoring all the renormalizations. I'm not putting them anywhere. You, of course, need this NLS to be what is called a weak order or reorder. And the reason is because if you have an infinite L2 mass, then the potential energy is infinity. And so it doesn't even make sense as a distribution, almost surely. So you have to sort of do what is called the first renormalization. And I'm ignoring it. And the uniqueness is in the sense that our solution is the unique limit of any possible choice of canonical approximations. And actually, a point of interest that will come at the end of the talk is that you see we barely miss. So this is S is strictly bigger than S, so we barely miss -1/2, which has a very special meaning or role in the context of Gibbs measures for NLS, and we'll come back to that. And so what Bjoern studied was the case of the 2D cubic NLS. And so he started with data which was strictly below. This equation, of course, is deterministically L2. The scaling is L2. So he started with data which was just below L2, because that's where the statistical ensemble of the measure is. And he proved actually that he had local well-posedness for that data. So that's a super critical result. Okay, so let me talk about the context of where Bjoern was. As I said, so if alpha is 1, then the random data looks like this. And then this corresponds always, so the map that sends omega into this Fourier coefficient always induces a probability measure, which is given by this Gaussian d-rho 1. And formally, you can write the Gibbs measure as the exponential of the Hamiltonian. There is a constant here that I'm fixing to be 1, which is beta, which is 1 over the temperature. That plays no role in my talk, so I'm setting it to be 1. And of course, this is total nonsense because I mean the Lebesgue measure there, but you know, this doesn't exist. But, you know. So you think of these things as sort of weak limits of finite dimensional approximations. So anyway, so the measure here, you could think of that as a weighted Gaussian measure, where the weight is given by your potential energy. And so what you want, when you construct your Gaussian measure, you always want this measure to be countably additive, okay? And there is a trace theorem that tells you that this measure is countably additive if and only if, in 2 dimensions, then rho sits just below it. It's a distribution that sits below L2. And in 3D, is a horrible distribution that is below -0.5. And this is the meaning that I want you to remember, that minus in 3D cubic minus 1 over p minus 1 is exactly -0.5. Okay. All right, so I'm not talking about the construction. The construction is a classical. So see, the notion of Gibbs measures is very nice because it's somewhere in between, or in the intersection of sort of like equilibrium statistical mechanics and sort of Euclidean constructive quantum field theory. I'm not going to talk about that because I know nothing about that. But Gibbs measures, or what is called the phi p plus 1D model, sit sort of intersection of those two things. So there is a lot of work, or classical works, that came from these communities that actually prove the existence, the construction, the rigorous existence of these measures. So in dimensions 1 and 2, the construction can be done for an EP, and this was done by Nelson in '66. And moreover, the measure is indeed absolutely continuous with respect to the Gaussian. That means that this measure is, so this is the Radon-Nikodym derivative, let's say. In dimensions 3, the construction can be done only for p equals to 3. This goes back to the work of Glimm and Jaff in 1973. But the measure now is singular with respect to the Gaussian. Okay? And this is very problematic. So it's a big problem. But actually, there has been work recently by Barashkov and Gubinelli, which actually gave us a better understanding of this support of this statistical ensemble of the measure. Because what they oops, sorry. What did I do? A mess. I don't know what's going on. Sorry. Yes. Good. Here, I don't touch anymore. Sorry, I cannot. Okay, my left. I'm not left-handed. But anyway, so what they prove actually is that it's singular, but it's absolutely continuous, not with respect to the Gaussian free field, but with respect to some random shift of this Gaussian free field. And there is a very nice variational construction of this. Okay, so in some sense, this gives some insight into how the measure, or the support of the measure, looks like relative to the Gaussian. And then in dimensions higher than 3, okay, there was a work in the 80s by Eisman and Frolix that said that if the dimension is bigger or equal than, this is all spatial dimension, the dimension is bigger or equal than 5, then the measure cannot be constructed. In other words, there is no non-trivial Gibbs measure. And for dimensions 4, this is the celebrated work of Eisman and Duminel-Copen in 2019, that they proved that the phi-4-4 model is trivial, also the marginal triviality, which means that it doesn't matter how you renormalize your nonlinearity, in the limit you will always get a Gaussian. Okay, you will never get a Gibbs. Okay, so okay, let me move on. So what we are interested in is not in the construction, but we are interested in the dynamics. So we are interested in, okay, how about the invariance of this, whenever the measure exists, how about the invariance under the flow, together with the existence of global strong solutions for data that is drawn from its statistical ensemble, from its support. And so the difficulty for the dynamics in dimension 1 is okay, but in dimensions 2 and 3, the difficulty stems in that you start with data that are distributions and that they are very rough. And so despite that, in dimension 1, this was done by Bjoern for an EP, and in dimensions 2, this is the result that I alluded many times before of Bjoern, where he actually proved for the first time that you can construct strong solutions in the deterministic supercritical regime. Now, for p bigger or equal than 5, the measure exists. Okay, and as I said, this is actually, if you take Park City lecture notes, Bjoern writes about this, that says, the measure exists and this should be true. I mean, it's like one should be able to do it. And I actually did discuss this with Bjoern in 2016, actually, just before. And so anyway, so the question is what happens, and I only wanted to treat the case p equals to 5, but actually what we discover with you, Deng and Haitian, is that we can actually treat all p's with the same method in a uniform way. And so this problem was open since Bjoern work until 2019, where we proved this, that actually also you have the invariance and the existence of global strong solutions for data that is sampled from the measure. And so how about d equals to 3, p equals to 3? This is actually the reason why this is too hard is because this problem is what we call probability critical. So when you are, I'll show you a picture in a minute, but when you are in dimensions 2 of p equals to 5, your measure always sits just below L2, and the scaling is, okay, for any p is minus 1 over p minus 1, which is below. So when you are sitting on the support of the measure, you are always subcritical with respect to this probabilistic scaling. But when you take d equals to 3 and p equals to 3, then you are exactly critical. Okay? So you gain nothing. So this problem is open and very hard. And today, actually, what I want to tell you is that of all the Gibbs measures that exist for nonlinear wave and linear Schrödinger, this is the only problem that remains open. Okay, so this is what I just said. Both this equation, both of these, this one, p equals 5, d equals 2, d equals 3, p equals 3, deterministically, they both scale like a half. But there is a big difference from the probabilistic scaling point of view. One is subcritical, the other one is critical. Okay, so
can I ask a quick question?
Of course.
But this probabilistic scale, though, depends on the randomization that you use, right?
Well, you do. Of course, it's going to depend. Okay, let me put it this way. It doesn't depend on the randomization. It depends on the geometry of this, on the underlying space, of course. I mean, if instead of periodic, you are on a ball or you are on RD. So on RD, you are much better. It's like minus 2 over p minus 1, like the parabolic one. And if you're on a ball, okay, you have your spherical harmonics. You're bound by whatever eigenvector, what are your eigenvectors of Laplace? Definitely. So, okay. So this is the statement of the result. That for any p, this is always true. And we have the usual properties that this is a global flow. This is what invariance means, that if you take sort of an initial ball of data and you flow it by your equation, then it preserves it has the same measure, or that any sort of initial data has the same, as a random variable has the same law as the evolve of the random variable that you have evolved. And so here is a little picture that you see Bjoern started, SG is the number where the Gibbs measure is supported, okay? So it's supported in SG minus minus, and that number is 1 minus d over 2, okay? So Bjoern started just below L2, and in order to solve this problem for NLS, NLS has no smoothing. So he's in 2D, so he started below L2, and somehow it's like that's the power of probability. He was able to show that somehow you can gain enough regularity to go over L2 and do your problem. And I'll show you in a minute how he did that. And so, but when p is 5, you have a much harder problem because you still start here, but now you have to somehow produce from nothing regularity that takes you all the way here. If p is 7, it's even larger, and so it gets worse and worse. Okay. So, and okay, I'll tell you in a minute why. Okay, let me go on. And so this is the same thing that I said before. When d is 3 and p is 3, then probabilistic scaling and this number coincide. So that's what we mean by critical. Okay, so how did Bjoern do? If I haven't, I mean, you probably are familiar with this, but if you're not, Bjoern, what he did is he did what we call a linear nonlinear decomposition, where he looked for solutions that have a specific form. They have the linear evolution of something that is random and rough. So this is going to sit below L2. Okay, there's nothing you can do about that. This is still the Schrödinger propagator is not going to smooth out that data, plus the remainder. And then what he said, well, thanks to tools. I'll talk about this in a minute. Then he wrote the equation for the difference. He wrote the equation for V, where you have interactions of things that are rough but random, and things that are deterministic but smoother, and using sort of multilinear large deviation estimates, counting estimates, And actually, this is very, very important, like random matrix estimates, where we call it TT star argument in harmonic analysis. He was able to prove that this V exists in a space of regularity that is positive. So V is in HS with S bigger than 0. So at the end, his solution is something that is below L2 plus something that is above L2. Okay? And actually, I want to emphasize this because this is actually, in some sense, the correct way of exploiting randomness when you have no regularity, no gain of regularity from the propagator. Okay, so why is it that this doesn't work when p is bigger or equal than 5 and work when p is 3? Okay, so let's suppose that we take p equals to 5. The deterministic scaling is a half. And we want to do like Bjoern, write it as linear nonlinear. But the point is that when you do this, in the best possible scenario, which is when you take interactions of everything random, the best place where you can put this V is below h1/2, which is still supercritical, right? So I cannot close by a fixed point argument the equation for V. So you cannot do this because Bjoern proved that this was above L2. So now this becomes subcritical and he can close. But in our case, when you're quintic, this remains below h1/2, which is supercritical. So you cannot close. So you can't do that. And so what is the poor regularity coming from? So when you look at the V, you realize that the poor regularity that doesn't let you go above h1/2 comes from this is a paraproduct. So it comes this Duhamel paraproduct. It comes from the high frequencies in the random term, linear term, and the low frequencies of this term. So when you are on the heat equation, and to some extent in the wave, because the Duhamel operator is smoothing, you can directly put this term in a nice space and close your estimates. But here it doesn't work, because in order to control the low frequencies parts of this term, this term contains this term, the powers of this. So to control the low frequencies of this, I need to control the low frequencies of this. And whatever I do, I never get out of h1/2 minus. You are always inside h1/2 minus. Okay, and so there is no way of controlling this term, assuming only regularity. Okay, and this is the point of I want to stop for a second because this is exactly the difference between what is called paracontrolled calculus and what we did. Okay, I mean here, paracontrolled calculus, you will stop. You will separate this term. You will put this term already in a better space, and then you will have a remainder. Okay. Okay. Questions? Oh, okay. So how do you get out of this one? So you have to put your hands. You have to get dirty and try to somehow peel off. A little bit, you understand better not just the regularity of V, you need actually to understand the random structure of V. You see, V is still random. It's just that Bjoern didn't need to use it. He could close using regularity, the regularity of V. But if you cannot use just the regularity of V, you need to understand the random structure of that V. Okay, and that's your only way out. So you need to somehow peel off V some more terms and understand the random structure of those before you get something that is smooth enough to close by a fixed point argument. And so, so this is what we introduced. We introduced this method of random averaging operators, and actually this method was a first step or laid the foundations for the theory of random tensors, which is what we use to solve the, sorry about that. Sorry. I shouldn't touch this. You probably cannot see these lines here, but there is some pink lines there. Okay. I cannot see them. But anyway, so the blue dot, so what is an example of these tensors and what is the random averaging operator? So the dark dot is simply, so f omega is the random data in the support of the measure, let's say. And this sub n means that I'm taking a Fourier projection at frequency n. So that's the blue ball. So e to the I this. So this is just a high frequency, high frequency of the linear evolution. And the pink, I didn't want to put red because okay, you know, high frequency, low frequency. So I put it kind of purple, but now I cannot see it. Now this corresponds to low frequency. Okay. So, for example, this picture, I just want to give you a little bit of a language, what this picture means. And these pictures, we draw them upside down than the parabolic people. So then when I show you the result on the wave equation, I'm going to make you crazy because I will turn all these pictures upside down. But let's see who's still awake. All right, so this is the Duhamel. For example, this picture means that I'm taking the Duhamel of the cubic interaction between a high frequency in the linear evolution and low frequencies here and here. Okay, and so this is an example of a 1-1 tensor, but it could also look like this or like this. All of these are examples of 1-1 tensors, right? You sort of like keep on iterating. Okay, so what is the random averaging operator? So the answer that we do is we say, well, the solution, instead of, I mean, the change of paradigm in some sense is that you don't want to think of that high-low interaction as an estimate of a term, but you want to think of that as if you're taking them all together, as if you're expanding forever, and you're thinking of that as an operator, as a random operator applied to the linear evolution. Okay? And so the answer that you make is that the solution looks like the linear evolution of your random thing plus the sum of all of these 1-1 tensors, which is nothing but the random averaging operator applied to the linear evolution plus a remainder. And what we prove is that actually, okay, you start below L2. That's where any of the powers p in 2 dimensions, the Gibbs measure sits there. You prove that if you start in H0 minus, then the p gains 1/2 derivative. So the p is sitting in H1/2 minus, which there is nothing you can do, so you leave it alone. Okay? And then the remainder now is good, because now the remainder is in H1 minus. And that's enough regularity in 2 dimensions to close by a fixed point argument. In other words, look at the difference between u and these two terms, which you control by hand, and you solve. Okay, and again, the tools that you use are similar to Bjoern, but there is something that we have to do here, which is actually a high order TT star argument, sort of like a, okay, I'll tell you that more later.
So what is the difference between what you're describing and simply saying that what you get in there is some distribution that's paracontrolled by the linear?
Because paracontrol is just one term and you're doing an estimate. And if you do just estimates on these terms, you'll never get out. That's what I'm saying. You stay always in H1/2 minus. You cannot get out. You can't close it. So I cannot close my argument if I look at this. No way. So you need to somehow put them somehow all together and change. You don't want to view them as estimating a term. You want to view them as an operator being applied to the linear evolution and estimate that operator as an operator, as a linear operator. So, okay, so the Fourier coefficient of this, actually, and this is the first very nice description of the solution that we get, is essentially you see the random data which you start, that's the Fourier coefficient, that's how you start it. And the second one actually is, so the HKK1 is what we call the 1-1 tensor, which is a matrix, and you can view it as a linear mapping sending, say, functions on K1 into functions of K. And we prove actually that this matrix is actually almost diagonal, is localized. Like it localizes like a Fourier multiplier. So essentially this term here, this is a Gaussian, this is like a color Gaussian, okay? And then you have a remainder. So that's to first order, I'm just giving you a description of how the solution looks like. Not just that it exists, but that's how it looks like. And what I should say here is that when you start on the support of the Gibbs measure, this decomposition, this random structure is for all time. Okay? The solution respects that structure for all time. It's global. And so what is the random tensor here? Well, the random tensor, what it does, is first of all, is independent on GK1, but what it does is it contains all the information on all the random information of the low frequency components of the solution U. Okay.
But you say your result is local in time. So you mean
no, this is global in time. This is the Gibbs measure result. For the Gibbs measure. For the other one that is local, I'll come now next. So when you start in the support of the Gibbs measure, this is exactly global. Okay, and Okay, and you gain a half because you start in H0. Okay, if you start, okay. All right. So we also, so here what I write here in a footnote is, of course, we globalize these structures. You see, there is a rubric which we call Bourgain's globalization argument, plus a stability result that tells us that these structures remain the same under small H1 perturbations of the data. So how do we prove the first theorem? How do we prove that? Now let's get out of the Gibbs measure. Let's take data which is very rough, as close as you want to the probabilistic criticality. Okay. And now the question is, do you have a solution? How does it look like? Okay. And this is what gives rise to this theory of random tensors. Okay, because now in order to solve this problem, we don't have to only expand to first order, but we have to expand to arbitrary high, finite but high order, okay, which gives rise to not just 1-1 tensors, but to 2-1 tensors, 3-1 tensors, 4-1 tensors, and this is just a way of organizing things, which all of these tensors carry the information on the the randomness of the low frequency components of the solutions, and they're always independent of the Gaussians that you have here. So again, you see what you have is a very precise description. These are the Fourier coefficients of the solution. This is our ansatz, because your solution now is going to look like, say, like before, the linear evolution. Then you have a matrix and a Gaussian. Then you have, say, a matrix, let's say in 3D, a cube, that is also localized as like a Fourier multiplier times the product of two Gaussians. Then another one that is like, you know, also kind of a matrix, maybe in 4D, that localizes like a Fourier multiplier times the product of three Gaussians, and so on and so forth. So in some sense, you could think that what I'm telling you heuristically is that if you sort of kind of like condition to the low frequencies, the high frequencies of a solution remain independent because they are the Gaussians. Okay. Plus a remainder that can be as smooth as you want, and is a small in L2. So now what I would like to emphasize for a second here is that what guarantees the independence is the fact that if you call Nj the frequencies of this, then in the ansatz, this in the maximum, you look at n is always the maximum of all of this, then these always remain above n delta, where delta is a parameter that you have. So you expand up to some threshold and then you stop. Okay. And this delta tells you where you stop. Okay. And so the fact that these nj's are bigger than this is what guarantees that you have this independence. Okay. So what I want to say is, okay, let me actually, before I put the next slide, say one thing. Is how big this expansion is. Well, how big this expansion is depends on how close you are to the probabilistic scaling. Okay. The closer you get, the longer the expansion. Okay. So the degree d here, which is the order of the expansion, depends on how far you are from this -1 over p minus 1. Okay. Okay. So the random tensors, where t we view as a parameter, are these highly nonlinear objects that allow us to sort of like control the complexity that are in these high order iteration trees. And they carry the information of the low frequency components of the solutions, and as I said, are independent of the Gaussians. Okay? The remainder is as smooth as you want. If you want to smoother, you just take a longer expansion. It's a small in L2. And of course, the convergence of this Fourier sum depends solely on the estimates that you can prove on your tensor. Okay? And this is what I said a minute ago, that heuristically the difficulty of covering the full range can be measured by the order of the expansion. Okay. Questions? Yeah.
Okay. So this low frequency coefficients, you think of them more or less deterministic, then, right?
They are random, and so we need to do random estimates on them. So there are two types of tensors. There's some deterministic, which is kind of like a base tensor that come from the structure of the nonlinearity. Okay, so they are just characteristic functions of whatever algebraic expression comes from the linearity, but then there are tensors that are like contain the low frequency of U, and these are random, and you have to treat them as random. The estimates are random. So, okay, so here is an example of a 2-1 tensor, for example. Now you will have two leaves, which are linear evolution of random, and one leaf that is low. Okay, and again, you see you have that if n is the maximum of n1 and n2, of these two, then you need this to be bigger than n to the delta, which is where you stop. And then the Fourier coefficient of this looks exactly like before. This is the matrix part. This is the, now what it will replace the random averaging operator. This is the 2-1 tensor. You see, Daniel, it has this term. The base tensor is just this, let's say. But this object has this term, and this is random. So you have to treat it as random. So this is what we call a 2-1 tensor, and is viewed as a linear mapping, sending k1, k2 into k. Okay? And k3 is strictly lower than this. Okay. So, okay, this is another example of a 2-1 tensor, but well, okay, just you can do whatever you want. There are many, many of them. So, what is it that we do? So as I said before, the theory allows us to get a handle on the complexity that arises from the higher order tree. And as I said, also, it's kind of like the analog, if you wish, to part of the regularity structure. And I say part because for NLS, we are fine with weak ordering. That's the only renormalization we need. In the regularity structures, there is one more ingredient which in the construction, which is that it builds the renormalizations into the method. And so far, we didn't need that. So that's kind of like something for the future. And so in order to prove our theorem, we need to develop an algebraic theory that tells you how do you construct these big tensors from smaller tensors. Okay, which we call merging, okay? And then we have another algebraic operation which is called trimming, and the reason is because when you put two tensors together, it can happen that some of the Gaussians fall below the threshold where you stopped. And if you do that, then you lose independence, and so you need to trim them, okay? So there is this operation called trimming that always guarantees that you stay independent, that the tensors they stay independent on the Gaussians, okay? I had some pictures, but I erased them because it was already too long. And then we also have an analytic theory. I can show them, it's at the end. So we also have an analytic theory, which is actually exactly choosing suitable norms that allow you to control these tensors and that they respect the algebraic theory, the merging and the trimming. Okay? And so the proof proceeds by an induction in frequency and an induction on the length on D, on the order. So it is a double induction. And so in some sense, these estimates is what allow you to control how you propagate the estimates in your inductive step. And so we rely on this induction plus multilinear large deviation estimate. There's a lot of counting estimates. There is a high order TT star argument, which is essentially you have to repeat what Bourgain did, but you have to repeat it like to a very large order. You have to take several TT stars, which are sort of like random matrix estimates. And there is a very subtle selection algorithm that you need because when you prove this algebraic, these analytic bounds, you have a lot of flexibility, and you need to choose the best possible estimate. You need to optimize and choose the best possible estimate you can get at each stage. And for that, you need an algorithm that tells you how to do that. Okay? And so maybe okay, I don't know if you want to see this. This is an example of how we do what we call a semi-product. So if you have three tensors, this is how you merge another. You construct another tensor. And so some of the estimates that you prove, you see the order in which you write these tensors doesn't matter, but the estimates do. So for each of these, as a mapping from BZ to ZW, you could prove an estimate of this form or an estimate of this form or many other ones. And which one you choose depends on where you are in your stage, in your proof. And so, so the formula for this stage doesn't depend on the order of this, but the estimates do. And so here is where the algorithm that optimizes the choice one makes comes in. And then what the TT star is, that comes, for example, for trim tensors. So the trimming means that if you have some Gaussians that have frequencies that fall below your n to the delta, then what you do is you contract against those offending Gaussians. And so here's, let's suppose you have an example like that. So this is a trim tensor. I mean, you have contracted. And so for these tensors, we prove what we call a random matrix estimate or moment method or whatever, which is simply doing, this goes back to Bjoern, and it's kind of like a TT star argument, but you don't do it only once like Bjoern. You have to do it like, the number of times that you do it is like 1 over epsilon. Okay. And you get an estimate. Okay, let me go on. So, okay, so let me go back to the Fourier coefficients. They look like that. And so at the end of the day, you prove estimates of this form. Okay, and this is enough to sum, because you see here you have the k of order alpha. This beta is something smaller than alpha, so this doesn't completely fully kill that. So you have this against that, you still have an epsilon, and so this allows you to sum. Okay, and this is what I said before, that we also prove for this sort of like some weighted Hilbert-Schmidt estimates that localize H as a linear multiplier. So all these tensors are localized. So what I want to say is that in the theory of regularity structures, the solution is obtained by a Taylor expansion with sort of like localized coefficients. Okay, and this is because you have the heat operator that localizes the operations, and these Taylor expansions are in terms of multilinear Gaussians. We also have expansions in terms of multilinear Gaussians, but on the Fourier side, not on the spatial side. And what is here localized, if you wish, are the tensors. Okay. Okay. Just breathe. I need some water. All right. This is part 1. And I don't know, I guess I have 5 minutes for part 2. Okay. I don't know, how long? You took like more than 5 minutes. No? I don't know. I didn't look. So, the invariance of the 3 Gibbs measure. Why is it that for the wave, we had a prayer of doing it? Because if you compute the probabilistic scaling for the wave, what you get is -3/4. In 3 dimensions, the measure is sitting in -1/2. So probabilistically speaking, this problem is again subcritical. So now you pray. Now you hope. And now it takes a lot of faith that this result is true to actually prove it. And actually, until we proved it, I mean, Gubinelli told me that, they thought it was not true. But it is true. Okay, so this is exactly saying that the cubic, if you take the equation, now you need a second renormalization. This comes from sort of like double resonances that appear in some quintic terms. I don't want to talk about this, okay? So you need an extra renormalization. I'm going to forget it. So the cubic nonlinear wave equation is now globally well posed with respect to the Gibbs measure, and furthermore, the Gibbs measure is invariant under the dynamics. So we have what is called the hyperbolic counterpart to the work of Herer, who give the local theory with the regularity structures, and Herer and Matesky, who proved the invariance of the measure. And for the nonlinear wave in 1 dimensions 1, this was done by Friedlander, and also this work by Sitkoff, but with some conditions. And in dimension 2, this is due to Bjoern, who is also in the Park City notes, and he does the cubic and claims that the P is the same. And then there's a paper of O and Thoman in 1920 who actually write the full proof. Okay, so formally the measure looks like this, and I don't want to talk about the definition, the rigorous definition of this. This is between quotation marks because you have to make sense of this. Okay, but you proceed by finite dimensional approximations, renormalizations, you take limit. And then you prove that these finite dimensional approximations converge to a well-defined limit, which is this measure called the phi4,3. So 4 is for the potential 4, and 3 is because of the dimension. You're in 3. Okay. So what is the problem that comes from the singularity of the measure? That the fact that the measure is singular with respect to the Gaussian gives you 2 headaches. Not just the fact, one is the spatial regularity, which is awful. But the other one is that now the Fourier coefficients of your data are not anymore independent because they're not Gaussian. Okay? They're all dependent. So it's a disaster. So these are the challenges to actually even get the local theory. And the goal is to separate these two challenges somehow, but keeping in mind also that you have to at some point globalize your theory. And so whatever you do, you shouldn't ruin somehow the rubric for globalization by trying to do this. So, but the hope is that you want to separate these two things by saying, okay, maybe I can find a representation of my data that has one part that is probabilistically very good, but very rough, and another part that maybe is pretty bad probabilistically because it contains all these dependencies, but it's very smooth. Okay. And so the way that you could try to do this in many ways, but the way we do this is by going through the heat flow. Okay, so what we do is we consider the cubic stochastic heat equation or the parabolic phi-4-3 model. Okay, and we know that this is well posed thanks to the works of Herrer and Guinelli and Keller-Perkowski. This is actually well posed, and you have solutions of this. And so the idea is that okay, you give me a sample of your data. Okay. And now instead of solving the wave equation, you first solve the heat equation. Okay, so you go from say time equals to 0, okay, that's you solve heat, up to time equals to 1. Like 1 is not 1, 1 is a short time, it's tau, whatever, but I'm calling it 1. And so now what you do next is you say, well, now I'm going to solve the wave equation whose data was not this phi, but is this data. And you're going to tell me what are you doing? It's like you're changing, if you can change the data, then you can solve anything. No, but you can do this because you already know that the invariance of the Gibbs measure under the heat flow. And so what that tells you is that the law of this and the law of this is the same. So I can change it. Okay. So what is good about this is that then you use sort of like a little bit of paracontrolled calculus that tells you that essentially now the data that you have can be written as the sum of three terms. High frequency is a Gaussian that has very bad regularity. Sort of like medium frequency is a sort of you should think of this as something that has Fourier coefficients which are cubic polynomials with different Gaussians. So this is a cubic Gaussian chaos and has a little bit better regularity. Okay, but a little bit worse probabilistically, and something which has all these dependencies. You don't know anything, but it's actually very good. It has regularity almost 1. Okay, and this is the data that we call is the caloric data. And so this just says that you could do it in another way, but this is the way that was best for us to be able to globalize. And then maybe what I just say about this is that now here. We need all the analysis of the random tensor theory, but we don't need the algebraic structure of the random tensors. Now, because thanks to the sort of like the smoothing of the wave, we can actually have what we call sort of like a model of a paracontrol answer, where you have some explicit objects. These are paraproducts. These are some. I'll tell you what they are in a minute, plus a remainder. And the regularity of this is the worst one. This is the linear evolution of the Gaussian. This is regularity minus a half. This is regularity 0. Then you have the green, this, and this. They are a half minus, and this is a half plus. And so what these objects are well, they're here. I mean, this is the linear evolution of that. This is actually the one that comes from solving this problem. The cubic K. This is the one that contains the heat propagator. Okay, and you have quintic objects and so on. These are the paraproducts. Okay, and I don't have time to show you this, but let me tell you two things about this. One is that there are terms which are infinity, okay, which are not removed by any of the renormalizations. And those terms are something that is the cubic quadratic and something that is like order 6. Each of these diverge, and you cannot kill them by renormalization. They are there. Okay, so here is where faith comes in, because then either you give up or you try to look for some structure, and what you find is that actually by themselves they make no sense, but together they have a well-defined limit. And this is what we call in our paper the 1-5. This is 1-5-3-3 cancellation. Okay, and then the other thing that is very beautiful is this interaction between heat and wave. And then I'll finish with this slide, is that then in order to solve for y, which is the remainder, you have to you have explicit objects which are very hard to control by hand. So we use this molecular analysis that was used by Deng and Haitian for the wave kinetic equation. And then you have non-explicit objects that involve inputs like these paraproducts. And here is where we have to improve our analysis, our tensor estimates, because the tensor estimates that we prove in our paper are linear. We view them as a linear operator. But here, and those are sharp, they're the best you can prove. But here there is one case only where they are, for the whole paper they are enough. But there is one case that comes when you take these three things, an input of these things, where is not enough. And so what you have to do is you have to prove something which is genuinely better and opens the door to a lot of questions, because we have to actually view the tensor not as a linear operator, but as a bilinear operator. And as a bilinear operator, it has genuinely a much better estimate. And so it's an open question of, okay, here we use what we know, but what can you do with this? Okay, and this is another key ingredient of the proof. And with this, I cannot be original, so, oops, I added balloons.
Okay, thank you very much for this nice lecture. Do you have any questions or comments in the audience?
Okay, I have a small question. In the decomposition of the wave equation, I didn't see where is the random averaging operator in this decomposition.
In here there is actually, okay, let me go back. There is no random averaging operator. So you have these explicit objects. This is like a paracontrol thing.
So it's a different method, right? It's
a paracontrol thing. You don't, that's what I said, you don't need the algebraic structure of the random tensor, so you don't need the random averaging operator, or you don't need the random tensors, but you use all the analysis. There are a lot of tensor estimates that you use.
Yes, I understand, but it's a different decomposition. So.
Yes, that's what I said. You don't need, there it is. I said, I think that is written there. It's a paracontrol answer. I didn't read it.
No, but because you said that we still need, no, you don't no longer need anything about the random average operator theory. Just use this Gobinelli decomposition.
No. But in order to close these estimates, you have to use all the estimates that we prove in the random tensor theory. All the random estimates, the tensors are here. They come in. Okay. They're not random, but we need the analytic theory.
Yeah, the delta that determines your power differential cutoff.
Yes.
Take it close to 1, or
for the random averaging. Okay, for the random averaging operator, you take it close to 1 because it's only order 1. For the random tensors, the longer you go, the closer to 0. Okay, and then maybe what I want to say one more thing is that besides the cubic, I mean, the only problem left now about Gibbs measure is the cubic NLS in 3D. Right, everything else we solved. The parabolic has been solved, okay? But there is another question that I find fascinating, which is, you see, we have a very good understanding of random structures in two settings. Either when you start, your data starts in the statistical ensemble of a measure, or that's global. We have a global understanding of the global structure, because this is also global. This is also global, okay? Or we have a very nice understanding of the random structure, but for short times, right? This thing that you are like Gaussian, color Gaussian, localized matrix 2 Gaussians and so on. But this is only for local time. And so the question that is interesting, this is what I would call out of equilibrium, right? Because I'm outside the Gibbs measure, and I don't care whether I'm close to the probabilistic scaling or I'm very far. You could take S as smooth as you want, but the question is, if for long times, how much of this structure survives?
Maybe one final question. Okay, Nicolas.
Yeah. So, for the wave equation, the deterministic Cauchy theory is completely insensitive to geometry. We also know that many of the Gibbs measures are insensitive to properties of the Gibbs measure are insensitive to geometry. So,
but for the linear wave equation, you do have problems, right? Because there's a lot of equations for which you don't reach the deterministic scaling, right? Because you have like Lorentzian symmetries or derivative nonlinearities. So there are cases on the nonlinear wave in which you don't reach the deterministic scaling. And the same happens actually for stochastic equations. In the stochastic heat, there is also cases which you don't reach it. For example, if you take noise which is rougher than white noise, even if you take the stochastic heat equation and the noise is rougher than white noise, you don't reach the -2 over p minus 1.
No, but my question was how much do you expect the wave equation result to be sensitive to geometry?
It should be. The scaling is totally sensitive to the geometry. That's, I think, a question that Daniel asked me, because it's the calculation I did depends on the estimates on your eigenvectors. So it's totally dependent.
What's your question?
No, what I say is that if you do, well, on the torus, what is good is that you can compute the product of eigenvectors that is still an eigenvector. But then what I say is that many of the properties, if you don't do it through eigenvectors, you can still prove that many of the properties of the Gibbs, the functions which are the support of the Gibbs measure, are still true. You don't see the geometry, because it's basically related to heat kernel estimates, which are completely insensitive to geometry. And so many of the properties of the Gibbs measure are true whatever the geometry is. And so my question is, how much do you think the results are going to rely on the particular thing on Tori is that the product of eigenfunctions is still an eigenfunction, right?
Well, but also it's this idea that I'm trying to tell you, that on the torus, right, the problem is subcritical. I don't know I didn't compute in another geometry what is the probabilistic scaling. I don't know. Maybe in another geometry it's not subcritical.
But you're looking at very high frequency. The geometry is basically Euclidean.
Yes, for Euclid, no, well.
The geometry in the scaling is, so you're looking, if you're on a manifold, you're just looking at the very tiny neighborhood of a point and then you're blowing it up, and the limit you're getting Euclidean geometry. So maybe the only question is that how heavily are you using counting estimates?
Very heavily.
So that might answer Nicolas' question.
Yeah, I mean, but it does rely on the counting estimates very heavily.
How much of a finer structure of counting estimates are you?
Well, I mean, very, very heavy, because I mean, it also depends on the nonlinearity. If I give you something quadratic, I'm dead. If I give you a quadratic nonlinearity, I'm dead. The counting estimates are horrible. So I mean, we are relying very much on that.
So I suggest that we postpone this discussion to the break. So we will resume in 15 minutes, and let's thank Andrea again.